You are going to use a state machine to design and implement in Multisim a binary sequence detector. And here's what mine looks like. And my binary sequence detector is looking for the binary sequence 0101111. Now, your binary sequence detector is going to look for a different sequence, but the design is going to be quite similar. And I'm going to go through and I'm going to enter that sequence, hitting the clock after each input. And you'll see that I will go through each state in my state machine. And at the end, my output light will light up because it recognized that sequence. So I will enter the sequence. Now I hit the key down. So when I enter 0 and hit the clock, you see I go to state 1. And then if I enter a 1, I go to state 2. A 0, I go to state 3. Now it's looking for 3 ones in a row. I go to state 4. State 5, state 6, my output light lights up. And if I enter something else, I'll go back to the beginning, and I will do that. I entered a 1 again, and I went back to state 0. And of course, if I enter the wrong input, I also go back to an earlier state, depending on what it is, and we'll go through how that works. So hang in there, and just a few slides, and then you're going to get to work on the lab. This is the state graph for my binary sequence. And again, my sequence is 0101111. So you can see that if I enter that correct sequence, starting from state 0, I go to the next state, right? I'm looking for a 0, I go to state 1, and then if I enter a 1, I go to state 2, 0 takes me to state 3, and then 3 ones in a row take me through states 4, 5, and 6. And finally, state 6 is my last state, and you can see in quotes here, I put the output. I'm outputting a 1 here, showing that I have completed the sequence. Notice all of the other outputs are zeros, right? I output a 0 until I have completed the entire 6-bit sequence. So let me fill in the rest of the arrows and you can see what happens. Now in each state, I could enter either the correct input that I'm looking for, and that would take me to the next state, or if I enter the wrong input, like if I'm in state 0, and I enter a 1, we could see what happens here. So if I enter a 1, well, I'm going to stay in state 0. That's not what I'm looking for. If I'm in state 1 and I enter a 0, well, I'm going to stay in state 1. I know you might think you go back to the beginning, but you don't, because 0 is the first bit in my sequence. So I just stay in state 1. I mean, that's the beginning of my sequence. If I'm in state 2 and I enter a 1, well, if I'm in state 2, I enter a 0, that's what I'm looking for. But if I enter a 1, then I have to go all the way back to state 0 because that's not the first bit in my sequence. So let's keep going. So if I'm in 3 and I enter a 1, that's what I'm looking for. If I enter a 0, since that is the first input in the sequence, this is going to be messy. I'm going to go back to state 1. So that's if I enter a 0. Same thing in state 4. If I enter a 0, I'm going back to state 1. Same thing for state 5. I think you're getting the idea. Now, state 6, same deal. If I enter a 0, that's the beginning number in my sequence, so I'll go to state 1. If I enter a 1, I'm going to go back to state 0. Now, your sequence is going to be different, but it's the same idea. You have to think about whether you've entered the correct bit in the sequence, and then you go to the next state, or if you enter the wrong one, you may go back to state 0, but you may actually go back to state 1 if it is the first bit in the sequence. All right, let's put it into a table and write the equations. This is the state transition table that I made from the state graph, which you just saw. Now, the first thing you might notice is that I have a couple of don't care conditions right here. Now, I'm going to need 3 flip-flops to build my circuit. That's because I have from state 0 all the way up to state 6, right? With three flip-flops, you can count from 0, 0, 0 to 1, 1, 1, which is a 7, but I'm not going to need state 7, right? I never get up to state 7, so I just filled these in as X's. These are don't cares. The rest of this table should be very familiar. The next state, I just got this right off the state graph, right? If I'm in state 0 and I enter a 0, I go to state 1. If I'm in state 0 and I enter a 1, I stay in state 0. This column, again, is just right from the state graph in the previous slide. The next state, this is very easy. This is just the binary representation of this state. So state 1, well, in binary, that's 0, 0, 1. State 0, obviously, is all zeros. State 2, for example, would be a 0, 1, 0 in binary, and so forth. You know how that works. DA, DB, and DC, I don't know why I made that a capital A, a little typo, doesn't matter. These three columns are the exact same as these three columns. Why? Well, because if you want a D flip-flop to output a 0, you've got to input a 0. And when the clock pulses, that's what your output's going to be. So since we're working with D flip-flops, yes, these three columns are always going to be the same as these three columns. So you can see that's what I did. And finally, my output, they're all going to be zeros. Again, this is exactly what I had in the state graph. All zeros, except when I get to my last state, they're ones to show that I have reached the end of my binary sequence. All right, now we're ready to write the equations. So here I have filled in these K-maps for my, my inputs to the state machine, DA, DB, DC, and my output, Y. And you know how this works. You've done this a million billion times. I'm just looking at the DA column, and every place there's a 1. I just fill that in my K-map, and then I circle the largest groups. And you know, here's this, you know how this works. So I circled this group, QA, not QB and X, and so forth. So once again, I'm just using the columns DA, DB, DC, and Y to fill in the K-maps, and then group the K-maps to get my simplified equation. And here again is my completed binary sequence detector, and you've already made something pretty similar to this. And I'm just very carefully wiring my inputs to my various D flip-flops, DA, DB, and DC based on the equations which I came up with. So if you follow these around, you can see they come from QA or not QA, or QB or not QB, and so forth. This, of course, is X and not X. And finally, at the end here, I have my output. Now, remember, my output was pretty simple. That was just QA ANDed with QB. Yours is going to be a little bit different, and I think you should be able to handle this lab. It's a little tricky, but I know you can do it. All right, get to work.